Okay, start with the chapter 3, coherent and non-coherent modulation techniques. Okay, in that I will move on to there are two techniques, and I will start first with the phase shift keying techniques using coherent detection. Okay, in that coherent detection methods, there are different PSKs or phase shift keying, binary phase shift keying, and quadrature phase shift keying, and so on. Okay, first, I start with the binary phase shift keying. In a binary PSK system, or in the bpsk in short form, is called as a binary phase shift keying. It has the pair of signals S1 of t and S2 of t used to represent binary symbols 1 and 0 respectively. S1 of t is represented by a symbol 1 and S2 of t is represented by a symbol 0, and which are represented in the form of a signals and a bit duration. And how to differ and how to represent the difference of the 1 and a 0 in the form of the energy and in the bit duration, as that is shown in the next. That is, S1 of t is represented in the form of energy and a pulse duration that is equal to square root of 2 times EB by TB into cos 2 pi FCT, that is over a one complete duration of the pulse, that is 0 to TB. And S1 of t has without a phase shift, or we can say phase shift is 0, or a phase is equal to 0, which is shown as equation number 3.1. And the symbol 0 is represented with the signal S2 of t, that is equal to square root of 2EB by TB cos 2 pi FCT plus pi, which is represented in the same way as S1 of t, but it has a phase shift of pi or a 180 degree, and which is simplified, that gives the minus of square root of 2EB by TB cos 2 pi FCT over one complete duration of the signal. And by comparing just, it is a 3.1 and equation number 3.2, and S2 of t we can represent as a minus of S1 of t. In this case, where TB is the bit duration, and EB is the transmitted signal energy per bit, and this energy per bit, and FC is the carrier frequency, which is equal to NC by TB, and where NC is some integer with respect to the carrier signal. A pair of signals which are represented in equation number 3.1 and in a 3.2, which are having the relative phase shift, or which are differed by a relative phase shift of 180 degree. And so such a signals, that is 3.1 and a 3.2, are called as the antipodal signal. Means the signals are a pair of a sinusoidal waves which differ by a relative phase shift of 180 degree, or called as the antipodal signal, which are shown in equation number 3.1 and a 3.2. This is what the symbol and a signal representation of the binary phase shift key. Next, I will move on to the signal space diagram of binary PSK signals. The binary PSK has only one basis function of unit energy, that is represented by pi 1 of t equals to square root of 2 by TB cos 2 pi FCT, that is for t is greater than or equal to 0 and is less than or equal to TB. As I seen in equation number 3.1 and 3.2, that is with respect we have the same expression within some energy, and here the basis function has unit energy, so EB here is considered as 1, so the equation becomes square root of 2 by TB. EB is equal to 1 here, okay, and which is represented by equation number 3.3. Express the transmitted signals. Now the equation number 1 and 3.2, that is S1 of t and S2 of t, in terms of a basis function pi 1 of t, as that is S1 of t equal to square root of 2 square root of root EB into pi 1 of t for a one complete duration, and the equation is represented as 3.4. And S2 of t equal to minus of square root of EB pi 1 of t, t is greater than or equal to 0 and is less than TB, which is represented by equation number 3.5. A binary PSK system is characterized by, binary means it has a two signals, M equal to two signals, but dimension is 1, which is less than the number of 1 less than the number of the signals, okay, so N is always less than or equal to M. The message points S1 of t and S2 of t are the symbols S1 of t and S2 of t, or the energies S1 E1 and E2 are located at S11 and S21 respectively. S11 means it has the first signal with a basis function 1, and it has the signal 2 or a symbol 0 with a basis function 1 respectively. And the signal space diagram for the PSK as shown in figure 3.1a. Just a minute, I will show you. And this is what the message point 1, and that is for a positive 0 greater than a 0 and a greater than 0, and minus root EB, that is message point 2, which is shown in the negative, and it has a two reasons, Z1 and a Z2 with respect to the decision boundary, and later I will discuss. And in the same way we have drawn the antipodal signals, that is 1, the symbol 1 is represented, it has started from the positive amplitude, and the S2 of t has started from the negative amplitude. That is what S2 of t is minus of square root of 2EB by TB, and so it is start from the S1 of t. S1 of t has started here. That is arrow mark I am showing. This is what the started from the positive energy. Okay, these are how the constellations are maintained in the next. Okay, move on to next. Okay, here, as I said, there are two message points. One is S11 and S21. S11 is the first message point, which is located at the positive side, and S21 is located at the negative side. That is with respect to the second signal S2, and which has the negative energy, which is shown in equation number 3.6 and 3.7. That is S11 equal to integration of 0 to TB S1 of t into pi 1 of t dt equal to plus square root of EB, and S21 equal to integration of 0 to TB, that is S2 of t into phi 1 of t dt, that is equal to minus square root of EB, which is shown in equation number 3.7. And now move to the figure 3.1b. The same figure 3.1b, That is already I have explained. That is showing. Okay, that is showing the example waveforms of antipodal signals representing S1 and S2. And just to go through the binary constellation of the figure 3.1, which has the minimum average energy, just we have gone, that is plus square root of EB and minus square root of it. Okay, okay, this is what the uh, representation of the signal diagrams. Okay, next I will move on to the generation of energy signals. This is what generation of the PSK signal. Generation of PSK signal, which are already we have derived these equations. This we are taking directly from the equation number 3.3 and 3.5, specifically which is shown in the block diagram of the figure 3.2a. One is the transmitter, that is called as the, usually the transmitter is called as the generator. In the next continuous or in the further sequences or in the further studies, the generator terms is understood is a transmitter, and generators are okay, interconnected words. We can use the transmitter instead of generator and generator instead of transmitter. Okay, which consists of two components. The first component is polar non-return zero level encoder, non-polar non-return zero level encoder. That is, I will show here in the down. Okay, now move on to, sorry, it's okay, it consists of two components, as I said, that is binary data, that is polar non-return 2-0 level encoder, and a product modulator. And I will come to the description of that. First one is the first block, as I shown, is a polar non-return 0 level encoder, which represents the symbols 1 and a 0. Just it represents, it's just a non-return 0 level encoder. What we have studied in the chapter 1, it is what we have done. It is 1 and a 0 of incoming binary sequence by amplitude levels of plus square root of EB and minus square root of EB respectively. And the second block, as I shown, that is the product modulator, which acts as an oscillator. This part acts as an oscillator. The product modulator, which is multiplying the basis function with the energy signal at energy that gives the binary PSK signal. They have described this thing. So this is what this multiplies the output of the polar non-return 0 encoder by the basis function pi 1 of t. In effect, the sinusoidal pi 1 of t acts as the carrier of the binary PSK signal, means we are sending the oscillator carrier frequency as a locked system or a locking or a coherent signal for the reception of the transmitted signal in binary PSK. Accordingly, binary PSK may be viewed as a special part of BSBSC modulation. Next, I will come to the what is the error probability of a binary PSK using coherent. To make an optimum decision, what is an error probability? Means, suppose if you are transmitting a 10 symbols, if it is receiving a 5 symbols, and here 5 symbols are lost and only 5 symbols are received, that is 5 by 10 symbols, means received are 5, transmitted are 10. This 5 by 10 means 50% are received. Suppose 5%, 10 symbols are transmitted, 3 symbols are received. That is 3 by 10. 30% symbols are. This is what the probability of an error means. How much is the signals which is not received? What is the sent and what will be the received? Is what the difference is. That is based on the probability. Means the chance of occurrence of an error or generation of an error in the binary PSK. To make an optimum decision on the received signal x of t in favor of symbol 1 or in favor of symbol 0. That is what? Estimate the original binary sequence at the transmitter input. We assume that the receiver has access to a locally generated replica of the basis function phi 1 of t. In other words, the receiver is synchronized with the transmitter as shown in the block diagram of a figure 3.2b, that is here. This is the phi 1 of t sent, the arrow mark is showing. Yes, 3.2b. We may identify two basic components in the binary PSK receiver. That has a correlator, that is what the multiplier, which correlates the received signal x1 of t, means that is finding the relationship or matching the signal which is received signal, that is x1 of t, with the basis function phi 1 of t on bit by bit basis. It is what? Bit by bit basis. Next is decision device, which compares the correlator output against to a zero threshold, which is assuming the binary symbols 1 and 0 are equiprobable. Equiprobable means they are equally occurring, means 1 and 0s are occurring equally. If the threshold is exceeded, a decision is made in favor of symbol 1. If not, the decision is made in favor of symbol 0, that is shown here in this diagram. If the threshold is greater than 0, then it will be considered that the message point 1 or a symbol 1, and if it is less than 0, it will be considered the message point 2. Next, move on. Apply the decision rule and partition the space. The figure 3.1 as shown in two reasons, as they explained. The set of points closest to message point 1 at plus root EB, and the second point is minus root EB, and which is constructing by the midpoint by drawing the line with the, that is acts as the decision reason, and it may be defined as two decision reasons or marked as the two decision reasons, and zone 1 and a zone 2, that is Z1 and a Z2. The decision rule is now simply to decide the signal S1 of t or a binary symbol 1 was transmitted if the received signal point falls in region Z1, means S1 of t, as that is the sent symbol was 1 if the received signal falls on the Z1. And to decide the signal S2 of t, that is what a binary symbol 0 was transmitted if the received signal point falls in the region Z2, means if the symbol is two kinds of erroneous decisions may, however, be made. One is, the first error kind is signal S2 is transmitted, means the signal 0 is transmitted, but due to the noise, there may be a there may be a chance of that symbol is falls inside the region Z1, means which is acting as a signal S1, so that the receiver decides in favor of signal 1. What we have transmitted is 0, but it will be considered as a 1. So this is what the first kind of error. The second kind of error is the reverse, converse. That is, we have transmitted the S1 of t, that is symbol 1 is transmitted, 1 we have transmitted 1 due to the noise or an error, that the received signal falls inside the region Z2 that is shown in figure 3.1a. So the receiver decides in favor of signal S2 of t, that is based on the threshold, and based on the threshold, just the decision, a decision device just decides the signal in favor, that is based on the threshold, and the threshold may be changing based on the noise. Right, this is what the second error kind. So to calculate the probability of making an error of the first kind, how to calculate the probability of making an error of first kind? This from figure 3.1a, that is already we have shown, that is the decision region associated with a symbol 1 or a signal S1 of t is described by, that is the positive region, the zone 1, and where the observable element x1, we consider x1 is related to the received signal x of t by, that is x1 equal to square root integration of 0 to tb, that is the received signal, which is the, that is oscillator frequency or a phase law pi 1 of t or a basis function pi 1 of t into dt. The conditional probability density function of a random variable x1, given that symbol 0 was transmitted, condition what it is here, the conditional probability density function means we are calculating with respect to symbol 1, but given that the symbol 0 was occurred, understood? Yes, and that is what the probability density function affects 1 here. So this is what x1 is, that is this is the transmitted, but occurred symbol is 0. Sorry, occurred is 1 and the transmitted is 0, which is equal to 1 by square root of pi n naught exponential of minus 1 by n naught x1 minus s to 1 square, because here 0 is transmitted, sorry, no, what is 0 is transmitted, so that we have used the here 2, but it has occurred 1, so this is x1 minus symbol 0, and this is the probability density function defined with respect to Gaussian random variable, okay, and which is represented by equation number 3.9. okay, and don't go in depth with this, just to remember this probability density function. Okay, using the above equation 3.7, that is what the definition of the zone, 3.7, that is what the, just a minute, this is s to 1, it has a negative EB, that is negative energy, with the help of that we will define the conditional probability that is in this equation, that is we can write there is x1 and minus square root of EB, this value minus square root of minus EB becomes a plus AB, and that is equation number, we can write it as 3.1. Just substitution of the energy which is defined in equation number 3.7. The conditional probability of receiver deciding in favor of symbol 1 given that in a similar way, that is the conditional probability of the receiver deciding in favor of symbol 1 given that the symbol 0 was transmitted, means the symbol 0 was transmitted but it is deciding in favor of 1, so that we can define this as P10, the probability of that is transmitted 0 and deciding as it is 1 shown here, that is, and this is because of the negative energy is positive, and putting Z in that equation, that becomes Z square, this substitution, just taking one substitution here and substituting the Z donor and changing the limits of that and substituting in that equation. And similarly we can express this as exponential of this complete function can be written as the Q function, is represented as a Q function of the energy with the N naught. Okay. Consider next an error of the second kind. That is what the first kind. That is what we have transmitted a 0, but the symbol 1 was occurred. In the similar way, the figure 3.1 way, that is already we have discussed, it depends on the zone. That is P01. That is we have transmitted the symbol 1, which is deciding in favor of the 0. Thus, averaging the conditional error probability, that is 1 is deciding with that is what we are sending 0, but it is deciding as 1. Another is sending 1 and where there is deciding as a 0. And now just you take the average of all these. This is called as the bit error rate for the binary PSK, which is shown here, and this is probability of error is equals to, that is taking 2 times it becomes, that is 2 adding those two, it gives the same Q function, this Q of square root of 2EB by N naught, same value we will get. This is what the first topic I complete and continue to the next topic further.